We spend a lot of time talking about algorithms as these sort of profound, almost magical recipes, right? Like you give the computer a set of instructions and it just bakes you a cake.
Yeah, that is usually how we think about it.
Right. But today we are starting with a pretty bold statement, I think. Algorithms can be profound, sure, but data structures can actually be deep.
Oh, absolutely. And it is a crucial distinction to make, really. We're moving away from just, the lift of instructions and looking at the physical architecture of the information itself.
Yeah.
Because when the data is structured correctly, the solution it just falls out of it naturally.
It does. And to guide us on this journey today, we have just a truly legendary stack of sources. We're looking at a 2024 Stanford lecture by computer science pioneer Dr. Donald Knuth.
A literal legend in the field, yeah.
Exactly. Alongside excerpts from his upcoming magnum opus, The Art of Computer Programming, Volume 4, Fascicle 12A, which, just the fact that he is still releasing volumes of this iconic series is amazing to me.
It really is. It's wild.
And we also had some brilliant visual deconstructions of an algorithm published by Robert Tarjan way back in 1973.
It is a phenomenal collection of material, honestly.
Yeah.
It covers this golden era of computer science while pulling it right into the present day.
So our mission for this deep dive is to explore Dr. Knuth's absolute, undisputed favorite algorithm of all time.
Number one on his list, yeah.
Yep. We are going to find out exactly how a computer can be dropped into a completely chaotic, just blindingly complex web of information and somehow perfectly map its entire global structure in a single flawless pass.
Right. And perhaps most impressively, do it without ever having a bird's eye view of the system it is navigating.
Which is crazy to think about.
It is. It operates entirely on local information, just completely blind to the big picture.
Okay, let's unpack this, because before we can really dive into the Explorer, we need to understand the terrain it's navigating, right? We are talking about directed graphs.
Exactly, the landscape.
And Knuth defines a directed graph incredibly simply. It's just a bunch of points, which we call vertices, connected by one-way arrows, which we call arcs.
Very straightforward.
Yeah, and in typical Knuth fashion, just to test his own algorithms, he actually built a test graph using the first 42 digits of pi just to randomly determine the connection.
Which I love. It highlights the reality of these structures, really. Directed graphs are everywhere in your daily life.
Oh, totally.
They are the internet, with links pointing from one site to another. They're supply chains. They're the prerequisites for the classes you took in college.
Right. You can't take 201 until you pass 101.
Exactly. And when we are trying to map this chaotic terrain, there are two fundamental types of structures we are really hunting for: strong components and weak components.
Okay, so if you're listening to this and trying to visualize a strong component, just think about navigating a city with a super complicated network of one-way streets.
Oh, that's a good way to look at it.
A strong component is basically the neighborhood where you can drive in circles without ever getting permanently stuck outside of it. It's defined by mutual reachability.
Right, you can always get back.
Yeah, if you can get from point A to point B by following the one-way arrows, and you can also find a path from point B all the way back to point A, they belong to the same strong component.
Mathematically speaking, it is a closed loop, a cycle.
A cycle, yeah.
And the brilliant thing is, if you take all the vertices in a strong component and shrink them down, like imagine collapsing that whole neighborhood into a single giant supervertex, you end up creating a directed acyclic graph, or DAG.
Because there are no more cycles left, right?
Exactly. Shrinking the strong components yields what we call a partial order. It just clarifies the flow of the entire system.
Okay, so that makes sense for the loops.
Yeah.
But then we have the other side of the equation, which are weak components. And this is actually where the history in our sources takes kind of a poignant turn.
It does, yeah. It's quite sad.
So in 1970, Donald Knuth and his colleague Ron Graham were exchanging letters with the Professor Motzkin. And Motzkin had discovered this mathematical concept of weak components.
A real breakthrough at the time.
But tragically, Motzkin passed away from a heart attack the very morning Knuth received his letter about it. It is just a sad but, fascinating legacy.
It really is. And the reason Motzkin's work was so revolutionary back then was that before this, connectivity in graph theory was mostly about reachability.
Right, finding out what connects to what.
Exactly. But Motzkin realized that unreachability actually forms its own rigorous structure.
Unreachability.
Yeah, a weak component is defined by mutual unreachability, or what they call incomparability. You have 2 points, and neither one can reach the other.
So no matter which arrows you follow, point A cannot reach point B, and point B cannot reach point A.
Right. They're totally isolated from each other in terms of flow.
See, I have to push back on this a bit, because if weak components are defined by the fact that they cannot reach each other, how is that a component at all? I mean, isn't a component by definition supposed to be connected?
Yeah, it definitely sounds like a paradox when you first hear it,
Yeah.
but it actually comes down to a deep mathematical principle called transitivity. We are looking at chains of incomparability.
Chains of incomparability.
Think of it like a project management schedule, right? If task A and task B cannot reach each other, meaning neither is a prerequisite for the other, they are incomparable. You could just work on them at the exact same time.
Okay, I see.
Now, if task B and task C are also incomparable, then by transitivity, A, B, and C all belong to the same weakly equivalent block. They form a chain.
Oh, wow. Okay.
And if you shrink these weak components down, you don't just get a partial order, you actually get a straight line, a linear or total order. You are essentially organizing the chaos into a strict step-by-step hierarchy of sources and sinks.
So strong components map out the interconnected loops, and weak components map out the strict linear hierarchies.
Exactly. You've got the terrain figured out.
Now that we understand the terrain, the real question is how a computer actually maps it. Because it's not like the computer can just, look at a drawing of the graph from above.
No, the computer's flying entirely blind.
Ha.
And that brings us to the primary vehicle for exploration, which is depth first search, or DFS.
And the sources use an incredible analogy for this. They describe the DFS algorithm as a spelunker exploring a pitch black cave.
It's the perfect way to visualize it.
You've got a headlamp, but it only lets you see the immediate tunnels right in front of you. You plunge as deep as possible down one path, and you have to leave like digital breadcrumbs behind so you don't end up walking in circles forever.
Right. But dropping a spelunker into a cave isn't enough on its own. The algorithm needs a way to actually categorize the tunnels it finds to make sense of the map.
Okay.
So it sorts them into 4 distinct types of pathways. And the way Tarjan categorized these arcs was crucial to solving the whole mapping problem.
Well, if I'm in a cave, I guess I'm essentially doing one of 4 things. First, I'm shining my headlamp into the unknown and just moving deeper into unseen territory. That would be the tree arc.
Correct. The trailblazing arc.
Or second, maybe I find a tunnel that provides a shortcut to a room I already know is further down my current path, like skipping ahead. That would be the forward arc.
Exactly. And the third is the cross arc.
A cross arc?
Yeah, this is a tunnel that cuts across to a completely different, already explored branch of the cave. It doesn't lead up, it doesn't lead down, it just bridges across to a different lineage entirely.
Okay, so we've got new tunnels, shortcuts, and cross tunnels. But the real danger, and I guess the thing we were actually hunting for to map those strong components, has to be a tunnel that loops back on itself, right?
Right, a tunnel that takes you back up to a room you've already been in on your current descent.
Yeah, exactly.
In graph theory, that is called a back arc, and it is the absolute proof that a cycle exists. It is the cycle prover.
Because if I can go deep into the cave and suddenly I find a tunnel that drops me right back into the entrance hall, I've obviously found a loop.
You have. But this is exactly where the algorithm hits a massive roadblock.
Yeah, there is a quote in the sources from Shimon Evans' book on graph algorithms that lays out this trap perfectly. He writes, "It seems like a circular situation. In order to compute the low point, we need to identify the components, and in order to find the components, we need the low point."
It's a classic chicken and egg problem. This is the obstacle that stumped some of the greatest minds in computer science at the time.
Because, if I'm in my maze and I find a tunnel leading back up to a room I've already been in, how do I actually know if I've found the absolute bottom of the cycle?
Right.
Or if I'm just in the middle of some massive nested set of loops? I can't seal off the room and call it a closed component until I know it's the bottom. But how does a blind computer know when to seal the room?
You were asking how a local observer can verify a global truth without ever seeing the whole map.
Yeah.
The legendary computer scientist Edsger Dijkstra actually tried to solve this exact circular paradox.
Oh, really? What did he do?
Well, his solution was brilliant, but it was heavy. It required adding 4 complex new arrays just to keep track of the overall structure.
4 whole arrays? That sounds messy.
It dragged the computer's memory down significantly. And then a young grad student named Robert Tarjan found a way out.
Ah, the secret sauce. This is Robert Tarjan's 1973 algorithm, the one Dr. Knuth loves more than any other.
That's the one. To understand Tarjan's elegance, we have to look at the explorer's toolkit, basically the anatomy of a node. Tarjan realized you don't need massive external maps or heavy arrays at all.
Okay, what do you need then?
You just need to give every single room in the cave 3 specific digital registers.
Like a little pocket watch for every room.
Yes, exactly. The first register is PRE. This records the pre-order time, which is the exact tick of the clock when the room was first discovered by the spelunker.
Okay.
The second register is PST. This records the post-order time. That's the exact moment the room was fully explored and abandoned.
So if I enter a room at tick 1, that's my PRE, and then I explore all its branching tunnels, and I finally leave it behind at tick 10, that's my POST.
Perfect. Now, the third register is the stroke of genius. It is called LW.
Oh, okay.
LW records the earliest PRE time reachable via any back arc from this room or its descendants. Basically, it tracks the lowest, oldest ancestor you can possibly escape to.
So as I'm pulling back out of the depths of the cave, returning from my spelunking, my algorithm is constantly updating this LW value. Like if I find a tunnel back to room 2, my LW becomes 2.
Yes. Tarjan engineered the algorithm so that as it pulls back up the path, it constantly checks a very simple equation. Does the node's LW value exactly match its PRE value?
Okay, so LW equals PRE. If I enter the room at tick 5,
Right.
and after exploring every single tunnel beneath me, the absolute earliest room I can possibly escape back up to is, well, tick 5.
Boom. When low equals PRE, a profound mathematical guarantee is triggered. The algorithm mathematically proves, using only that local pocket watch data, that there is no escape route higher up the tree.
Wow.
This room is the definitive leader of a sync component. It is a black hole. Nothing escapes further up. And the moment that condition is met, the component is immediately sealed and settled.
But wait, how does the physical mechanism actually grab that component and seal it?
Through an incredibly elegant stack mechanism. As nodes are discovered on the way down, the algorithm pushes them onto a sync stack. Think of it like stacking plates at a buffet.
Okay, piling them up.
Right. You keep putting plates on top of each other as you go deeper into the cave. When that LW equals PRE condition hits, the algorithm knows it has found the bottom of a cycle.
Right.
It looks at this stack, and it pops all the plates off down to the leader simultaneously. Every single node placed on top of that leader belongs to its closed loop. It seals them all together in one clean move.
Okay, here's where it gets really interesting. Because you are only pulling plates off the top of the stack, you are naturally finding these sinks from the deepest part of the cave backwards to the entrance.
Exactly.
It is naturally extracting the components in perfect topological order, like it processes them from right to left. And it does all of this completely locally. The node itself encodes a global history using only its own local data.
Yes.
It just looks at its own PRE and low W values and knows it's the leader.
You've just hit on exactly what Dr. Knuth meant at the beginning of all this. This is why data structures can be deep. The node isn't just holding a static value.
No, it's alive in a way.
Right, its very state, its L node W and PRE numbers,
Yeah.
perfectly reflect the global reality of the chaotic web around it. The architecture of the data solves the problem before the algorithm even really has to think about it.
That is just incredibly clever. It's almost like a form of algorithmic judo, like using the structure's own weight to sort itself.
It really is.
But we are actually only halfway there. We've found the strong components, the loops. But what about the weak components? Those linear hierarchies of incomparability we talked about earlier. Did Tarjan just, stop at the loops?
Oh, he definitely didn't stop there. In 1974, Tarjan published an update that unified the entire process. He realized that because the stack mechanism settles the strong components perfectly from right to left, you can actually determine the weak components dynamically, organically as you go.
Wait, if the strong components are already settled, how do you string them together into a linear hierarchy?
By observing collisions.
Collisions.
Yeah. As a newly settled strong component is finalized and pulled off the stack, Tarjan's updated algorithm looks at where its outgoing arrows point. It literally watches how the new component hits the sources of the existing, already settled components.
Okay, let me visualize this. So I'm building my map from right to left. I just sealed a new strong component. Let's call it component V. If component V has no outgoing arrows to any existing components, like it didn't hit anything, it just becomes an isolated weak component all by itself.
Spot on. But if component V has arrows that hit all the sources of an existing weak component, it merges seamlessly into that existing hierarchy. It simply becomes the new source, the new head of that line.
Interesting. But what happens if it hits multiple different hierarchies at once?
Then they merge violently together. The strict boundaries between those separate weak components collapse entirely, and they form a single, massive, new weak component, with V sitting right at the head.
Oh, wow.
By simply watching these local collisions happen organically as the sync stack pops, the algorithm perfectly categorizes the weak components without ever having to rescan the whole graph.
Wait, but if it's constantly checking these sources to see what got hit, doesn't that slow the computer down? I mean, if an existing component has a million sources, scanning that list every time a new component pops off the stack sounds incredibly inefficient.
And that is exactly why Tarjan introduced a technique called lazy deletion. He added two tiny 1-bit flags to his nodes, HIT and white. Just a 0 or a 1.
Oh, so instead of the computer having to pull out a massive ledger and check, like, have I been to room A, room B, room C, Tarjan just sticks a physical do not enter sign on the door.
Exactly. A single bit of data flipped from a 0 to a 1.
That's brilliant.
The WIT flag is set to 1 if there's an arc to this node from the currently active vertex. But the HIT flag is the real hero here.
How so?
If a node has been hit by a new component, it is permanently marked with a 1 in its HIT flag. This means it is no longer a source. The computer sees the 1, doesn't even open the door to check the ledger, and just keeps moving. By using this lazy deletion, the algorithm mathematically guarantees it never traverses a long list of sources twice.
So combining that LOW equals PRE trigger, the stack mechanism, and these tiny 1-bit lazy deletion flags, what does that actually look like in terms of final efficiency?
It achieves total structural mapping in exactly one linear pass. Specifically, it guarantees at most 5 meters plus 17 memory accesses. That is 5 accesses per arc and 17 per vertex.
And memory access is the true metric of algorithmic efficiency, isn't it? It's not just about raw speed.
Absolutely. CPU cycles are incredibly fast and cheap, but fetching data from memory, like actually asking the RAM for a piece of information, is comparatively slow and expensive.
Right.
By putting an absolute mathematical ceiling of 5 meter plus 17n on those memory fetches, Tarjan ensured flawless efficiency, regardless of how chaotic the graph is.
You know, Knuth talks about this specific efficiency in the Stanford lecture. He has this famous philosophy where he says, premature optimization is the root of all evil.
A very famous quote in coding, yes.
Right, like programmers shouldn't waste time making code slightly faster if it makes it unreadable or broken.
Yeah.
But he looked at Tarjan's 1974 algorithm with its lazy deletion and its recycled data fields, and he actually calls it post-mature optimization.
Which is such a great phrase. It is a mature, perfectly distilled artifact. It is a result of taking something that already works beautifully and just squeezing absolute perfection out of it by deeply understanding the physical hardware it runs on.
But I mean, we are always taught that code should be beautiful, simple, and readable, right? And Knuth admits that Tarjan's optimized code looks messy.
Oh, gosh.
It's full of trickery and subtle variables doing double duty. So if this optimization makes the code look messy and hard for a human to read, isn't that a bad thing?
Well, Knuth's counterargument to that is really profound. He points out that the computer doesn't slow down when it reads tricky code. When the computer comes to a part of the code a human might not understand, it doesn't hesitate. It accelerates.
Oh, wow.
True algorithmic beauty isn't just about human readability. It is about creating a data structure that flawlessly does two things at once. Every variable, every 1-bit flag, has a profound mechanical purpose. The subtlety is exactly what makes it deep.
The computer doesn't slow down for elegant subtleties. It accelerates. That really reframes what we consider to be a good design.
It is a stark reminder that we are building architectures for machines, not just narratives for humans. Tarjan's algorithm is beautiful because of its mechanical perfection, not its prose.
So what does this all mean for you listening to this right now? Because we have gone on quite a journey today.
We really have.
We started with the blind spelunker dropping digital breadcrumbs in the dark. We watched as simple nodes were given the power of deep global awareness through their PRE and low registers. And we saw how a flawless mathematical sweep could perfectly sort a chaotic web into strong loops and linear, weak hierarchies.
And you know, the value of this goes far beyond just computer science.
How so?
Well, when you look at your own task list, or you are managing a massive, tangled corporate project, or honestly just trying to clear out your own mental backlog, there's immense value in finding your sinks.
Yeah.
You have to find those closed loops, settle those dependencies, and sort them out linearly.
It's about finding the Tarjan algorithm for your own life, really. Settle the sync components so you can actually move forward.
Exactly. And if we connect this to the bigger picture, I'd like to leave you with a thought to mull over.
Let's hear it.
Tarjan's algorithm proves, mathematically, that you do not need a bird's eye view to perfectly map a global system. You only need the right local rules.
Mm.
It makes you wonder, what other complex systems in our world might be secretly coordinating their massive global structures through entirely blind local interactions.
Oh man, economic markets immediately come to mind for that. Millions of people just checking their local prices, basically creating a massive global structure without a master blueprint.
Or the billions of firing neurons in our brains.
Yeah.
I mean, they don't have a map of the whole mind, yet they create consciousness.
Just nodes in the dark, checking their local registers, and
Mm.
perfectly mapping the unknown. Usually, when we talk about algorithms, there is this expectation of a top down command. But Tarjan shows us that if you design the room right, the maze just solves itself.
Thank you for joining us on this deep dive.